Right. Hello and welcome. In this video, we're going to look at this RLC parallel band stop filter. We know it's a band stop filter because all of our input voltage goes across this first resistor, hits this parallel node, and anything that the inductor and the capacitor will allow through is going to go directly to ground away from our output, and anything that's left over from that is going to be allowed to go through, right? So it's going to stop whatever frequencies that it allows from actually entering out to the output. So that is the goal for this. So we are going to start off with our frequency output, so our F value. And they want the exact center frequency, and so we got to use the entire winding resistance for this one. So that's that long equation, square root of 1 minus our RW, our winding resistance, squared multiplied by our capacitor, divided by our inductor. The entire thing here is going to be divided by 2 pi. And then our square root of LC for our time constant. And that's because we have both inductors and capacitors in here. So we can plug that in. We have all those values. So we'll start off with our square root of 1 minus our open parenthesis here for our winding resistance of 22 squared. And that is multiplied by our capacitor 0.03 times 10 to the negative micro is 6. And after that, we'll close that parenthesis and divide by our inductor value of 22 millis. We'll move that out, 0.022. And then that entire thing gets divided by our 2 pi square root of LC. So that's our 0.022 multiplied by our 0.03 times 10 to the negative micro 6. All right, so we got our frequency out. So we'll set our frequency equal to 6,193. They want it in kilohertz. Our decimal point's right here, so move it forward 1, 2, 3, and we'll keep 3 numbers out of this. 6.19 kilohertz. All right, and so that's our first answer. We'll type that in, 6.19. After that, we can use that to figure out our Q. Remember, our bandwidth, BW, is equal to our resonance frequency, FR, in this case, that's what we just got here, divided by our Q, and our Q is equal to our components, right, our inductive components. And so XL divided by our winding resistance, in this case, RW. And we need to find XL first. So we'll set XL is equal to 2 pi FL. We just found out our frequency, so we can plug that in. We'll say that we have 2 pi times our frequency of 6190, that's our full frequency that we rounded to, multiplied by our inductor value of 22 millihenries, so 0.022, and that gives us 856, and that's in ohms now. So we can plug that into our Q over here. Let's change the color so we can keep track of where we're at. So our inductor is 856 ohms. We'll divide that by our winding resistance of 22 ohms. And that's going to give us our Q. And so we'll set that out. So 856 divided by 22, 38.9. So we can round that up also. We'll set this equal to 39. It doesn't have an ending because it's just a factor. And then we'll go after our bandwidth. So our bandwidth is equal to our resonance frequency, so 6190 divided by our Q of 39. And that's going to give us our bandwidth range. So 6190 divided by 39. It's 158. And we'll round that up, 159. And that's in hertz. Right? That's what they expected it to be in hertz, not kilohertz, so that's good. So 159 is our output. And so let's check that. There we go. Okay, let us know if you have any questions.